grade 12s, welcome to physics class. Friday morning, May the 15th. Hope you had a good day yesterday. And today we're going to continue our discussion about resistance, and what we're going to get into today is the beginnings of analyzing electric circuits. But before we get to that, our verse of the day today comes from 1 John 3:18, where it says, "Dear children, let us not love with words or speech, but with actions and in truth." And so again, just a reminder to love one another. Not that we shouldn't love with our words or speech, but our actions and our truth and in truth are important as well. So keep that in mind as we go through the day today, and you strive to serve one another, however that looks. All right, just before we get into what we want to cover in circuit analysis, we want to talk a little bit about question 2 from your assignment yesterday, the second question 2 in the parallel section. Just to make sure that we're getting this. Here the question said, find the equivalent resistances for a number of 60 ohm resistors. It wanted the equivalent resistances for 2, 3, 4, and n number of resistors. So remember, when resistors are connected in parallel, this is the relationship. 1 over RT, R total, equals 1 over R1 plus 1 over R2 plus however many resistors there are. Now, if they're all 60 ohm resistors, it becomes 1 over RT equals 1 over 60 plus 1 over 60 plus 1 over 60 and so on, as many resistors as there are. That could be simplified to 1 over RT equals N, the number of resistors, times 1 over 60 ohms. And so this becomes a bit of a formula for this particular question. And so that if N equals to 2, we get 1 over RT equals 2 over 60, which I've already reduced to 1 over 30, meaning our total is 30. Okay, so if we had two 60 ohm resistors, it would be equivalent to a single 30 ohm resistor. If N equaled to 3, if I had 3 60 ohm resistors, it would become 3 over 60, which I've reduced to 1 over 20, meaning that the total resistance would be 20 ohms. Okay, so if we had 3 60 ohm resistors connected in parallel, it would be equivalent to a single 20 ohm resistor. I didn't do the N equals to 4 because I'm sure you can do it. Put 4 in, you get the answer of 15 ohms, and then again the final answer was exactly this formula. This is the relationship between the total and the number of 60 ohm resistors. All right, hope that makes sense. We're going to start doing some circuit analysis now, so we'll go to the other board and we'll set that up. All right, here is the first circuit that we are going to analyze. Now, when we analyze circuits, we are only using our knowledge of Kirchhoff's laws, the voltage law and the current law, and Ohm's law. And so we'll be using the formulas for the resistors, whether they're in series or parallel, and we'll be using Ohm's law. Those are the only things we'll be using. And when we want to do circuit analysis, what we want to find is we want to find the potential difference, the current, and the resistance of each element in the circuit. Okay, so when we have a circuit like this, we've got the total circuit. We want to find the elements for the total circuit. And then we also want to find those three things, potential difference, current, and resistance, for each of the 3 individual resistors. The best way to stay organized, in my mind, is to always create a table like this. We've got VIR across the top, potential difference, current, resistance. We've got T for total, and then resistors 1, 2, and 3. And if we do this and we write in the information that we know, it's a good way to begin and be organized. So we have 60 volts as our total potential difference. We have 6 ohms. We have 10 ohms and 8 ohms. All right, now it's our job now to fill in that chart. So this becomes the question now. Find all the missing pieces in that chart. So when we look at this, we have to decide what is it that we can find. And we only find the things that we can find, right? No point in trying to find things we can't, so let's find the things we can. Because I have the 3 resistances, I can find the total resistance, right? We know we have 3 resistors in series. We know how to do that. You don't have, because it's just adding, you don't have to write this out, but it's a good idea to always show your work anyway. So RT is simply R1 plus R2 plus R3, or 6 ohms plus 10 ohms plus 8 ohms. And if we do our mental math properly, you can add those numbers, we get 24 ohms as our total resistance. All right, now we look at our chart again and well, what can I find? Well, if I have V total and R total, I can find I total. All right, let's find I total. So I total is equal to V total divided by R total. So 60 divided by 24. That gives us a total current of 2.5 amps. Okay, so I put that in here, 2.5 amps. Okay. Now here's where our knowledge of Kirchhoff's laws come into play. These are resistors in series. Kirchhoff's law says that the current does not change as it flows around a circuit. So the three resistors have 2.5 amps flowing through them all. Okay. And then that leaves us some simple calculations to solve for the potential difference of each of those resistors. We'll simply be using V equals to IR, and we'll be multiplying the numbers together. And so 2.5 amps times 6 ohms is 15 volts. And the next one is 2.5 times 10, 25 volts. Now this one you can do in two different ways. You can do 2.5 times 8, or you can do 60 minus the other two, but either way you are getting 20 volts. And once we've filled in the chart, we are done. All right, now this is a fairly simple one. Let's do another example where we add some more elements to it. All right, here's our second example, and in the second example we're looking at a parallel circuit. And so in this particular one, again, we have a potential difference source, a voltage total, and then R1, 2, and 3. And we're given the currents that run through R1, 2, and 3, remembering that they're different because they're parallel. All right, here's my chart again, VIR, the total, 1, 2, 3. Let's write down what we know, and what we know is the currents. We know 2 amps here, 4 amps here, and 6 amps here. Okay, all right, so from this information we can find the total amount of current. Again, Kirchhoff's law for current in a parallel circuit simply says that I total has to equal the sum of the three other currents. And so we're going to get 2 plus 4 plus 6. And again, I hope you can all do that math to get to 12 amps. And I was going to use the blue marker to put in the numbers that we found. So 12 amps. There we go. All right, now what else can we find here? Oops, I forgot to write down a piece of information that we know. We need to know at least one other piece, and that piece is that R3 equals to 8 ohms. All right, so there's what we know, and now let's go ahead and let's find V3, because we can, right? Again, remembering that V3 will equal to I3R3. And I won't do that calculation there, but here we got 6 times 8, which is 48 volts. Okay. Now here again is where we have to use Kirchhoff's laws. Kirchhoff's voltage law for resistors in parallel says that these three have the same potential difference. So R1, 2, and 3 will have the same potential difference, and that is obviously 48 volts. 48 volts for both of those. Okay, now because they're all 48, that also means that this is 48. Okay, so what we remember here is that when the current goes through the parallel part, that's the drop in potential difference. And so if I'm dropping 48 volts here, the increase must be 48 volts here. Okay, so we have 48 volts here as well. And now it's pretty straightforward to find our resistances. all we need to do is divide. Remember that R will equal V divided by I, and we can solve for all of our resistances. Okay, and so where do we have those here? Oh, this question didn't even ask us to find R1 and R2. Okay, so let's find the 48. This is 12 ohms. This is 24 ohms. And then to find the top one, again, we would do 48 divided by 12, which will be 4 ohms. And again, this 4 ohms you could find by finding the equivalent resistance of these 3 resistors here. You could, we're not going to do it, but you could do 1 over RT equals 1 over 24 plus 1 over 12 plus 1 over 8. But again, why would you do that when you have a much simpler method of just doing 48 divided by 12? Right? Okay, so that's a parallel circuit. Okay, remembering that in a parallel circuit it is the potential differences that stay the same, while as in the last example we did, the current was what stayed the same because it was a series circuit. Now, what happens if we have a series and a parallel component within the same circuit? We'll do that on the other board. Alrighty, ready for next example number 3? So in this example, we have a resistor that is in series with the circuit, and then we have this part here that is in parallel with the circuit. So we have a series, something that is in series, and this parallel part is considered to be in series with this part. So we have sort of 2 sections here that will combine to make one circuit. All right, so we have a 120 volt source, we have 12 amps leaving from it, total amps. We have a resistor 1 with 8 ohms, R2 we don't know, R3 is 3 ohms. There's our chart. I filled in the information that we already know. And so we're ready to start solving this again, keeping in mind our laws and Ohm's law. So first thing we're going to do is we're going to find the resistance here by doing R equals V over I, and that's going to give us 10 ohms. All right, let's get starting point. And once we have that, we are now going to start filling some information. So the other things that we know right off the bat is we know that this R1 has 12 amps flowing through it, right? If 12 amps leaves the source, 12 amps is flowing through here. That allows us to find the potential difference, V equals IR, and get 12 times 8 is 96 volts. All right, once we have that, what we're going to want to do next is we're going to want to find the potential difference drop for this parallel part. Okay, so we have 120 volts coming here. We have 96 volts being used here. The rest gets used up in this parallel part. And so the rest, 120 minus 96, is 24 volts. And 24 volts is the voltage for the parallel part. So both resistors in the parallel part have a potential difference of 24 volts. That allows us to find I3, the current flowing through the third resistor. And so 24 divided by 3, and I equals V over R, and that gives us 8 amps. And if I look back at my circuit here, if I have 12 amps coming into this joint here, and I have 8 amps going one way, Kirchhoff's current law says that I must have 4 amps going the other way. So this becomes 4 amps, because 8 plus 4 has to add up to 12. And then the final piece is the resistance of R2, and that will be, again, R equals V over I. So 24 divided by 4 is 6 ohms. Okay, I didn't show any work for that, because it's fairly straightforward work, and you wouldn't have to necessarily either. But the thing is, if you don't show work and you get answers wrong, it's hard for me to give you part marks. So feel free to make sure you show some work. This was fairly easy, straightforward math. I'm pretty confident that I can multiply and divide numbers, although I've been known to make the odd mistake. But if you're fairly confident you can do that, great. You don't need to show work. If you get those right, I'm going to give you full marks for it. If you get them wrong, show some work, maybe I can give you part marks. If not, well, then you just got it wrong. All right. I'm going to give you an assignment to work on, a few more of these, and we're going to spend a couple of days doing these, getting some increasingly more difficult circuits to analyze. Okay, all the ones we did today were 3 resistors. We can have as many resistors as I can imagine in a circuit, and we can have a bunch of combinations of parallel and series, and they'll get increasingly harder. So we're going to spend a couple of days doing this. So we'll start with the assignment today, probably do another one Monday and maybe Tuesday as well. So have a great weekend, work on some of this, and we will see you on Monday.